Okay, can everyone hear us on Zoom? Just like a thumbs up or something.
Yeah, we can hear you.
Okay. Okay, hello everyone and welcome to this week's colloquium. Today we are pleased to have Dr. Gourab Giri. He is a postdoctoral fellow now in Italy, INAF, and he is visiting SAAO for his research visit, I think for duration of 2 months, right?
Yes.
Okay. So yeah, today he will be talking about analyzing unusual radio outflows in extended radio galaxies.
Yeah.
Thank you so much, Gaurav, and the floor is yours.
Okay, cool. Okay. So, okay, we will have a close discussion then. So, I am basically working on a project which I named it. There is no funding yet. It's called AURORA. It basically stands for Analyzing Unusual Radio Outflows in Extended Radio Galaxies. And this is a project basically to it's a theoretical project, but it works as a synergy between theory and observations, data, and also go back to numerical simulations, theory, and observations. Now, it only focuses on distinct sources, peculiar one, because they give more physical insights than normal straight jets. So anything distinct, I'm there. Now, just to tell you about why distinct sources are interesting and where we are lying in current epoch. I'm just giving you a collage of sources that have been reported in 2024 to my knowledge. I mean, I don't know the entire literature, of course. So you see, this is a peculiar radio galaxies with straight jets, and then the jet bends completely opposite end, which we don't know what's happening. Most likely, it's a instability that is happening over there in the jet. But such things, when you see in a giant radio galaxy, then things get complicated because giant radio galaxies are typically believed to reach their age of the environment that they reside. Then you can see maybe there is a older lobe along east-west directions, and then suddenly the current jet flips to almost 90 degree, and it's a flipped jet. But the question is that how you can explain a 90-degree jet reorientation and your jet still is ejecting, it's not ending, there are also 7 megaparsec jet, which is discovered 2024. This is the largest known jet known currently to the literature. And 7 megaparsec means that it just don't reside. I mean, it's almost the size of the cosmic scales, voids, Now, how can you produce them? Second, other aspects are, for example, this is a source which resides in the edge of the cluster, and because there is buoyancy and other effects working, so usually it's an X-shaped radio galaxies. You have east-west or nearly east-west current epoch of jet activity, but then there is the older epoch, which is supposed to be a straight line bidirectional, but then the other one is vanished. There is also other examples. For example, this is a reorienting jet, but you can see the scales. It's 8.7 kiloparsec, and that means it's a tiny one. And the host galaxy is a spiral galaxy. It is believed that reorientation typically happens in ellipticals because they are susceptible to galaxy mergers. So there are two black holes which will come. But something that is happening in spiral galaxies are interesting now. Okay, so this is all happening 2024, and we are in 2025. So that means we have machine learning techniques now to detect peculiar sources all over the sky, because I think majority of the sky patch are scanned by either of the telescopes, so data are publicly available. You used ML techniques, and then there are 700 sources. For example, this paper come up with a single field. It's MGCLS most likely, Meerkat Galaxy Cluster Legacy Survey, and they come up with like 700 sources right there. So now with this massive amount of data, where we are going then? Like there is serious need of understanding what physical mechanisms these jets can give you, because all you can see is a radio image, and lots of information are missing: optical, x-ray, infrared, dust, so what I am proposing basically is that before SK come and start scanning the southern sky, because LOFAR has already done for the northern sky, 46% sky is already covered, and this data will be public soon, maybe next year. So SK will come and scan the entire sky with very high resolution. So I think we are going towards an epoch where single source reporting or statistical source reporting is old fashioned, and we need a theoretical backup to every source to understand the universe and model what's happening for each sources. Just to give you an idea that whether modeling of these peculiar sources are even possible with current techniques that we have, I think we have it all. Straight jets, for example, you see Cygnus A, which is normal standard kiloparsec scale jets, and then you have the giant category, which are GRGs, which reaches almost like more than 700 kiloparsec and then beyond. I don't know where is the limit. We don't know right now. Straight jet modeling is easier, and you can see the paper 1993. This is the paper from where the jet simulation started. So we are now like 25 years of experience or more. What about the bend ones? You can categorize them. For example, this is a straight jet and this is a tailed category. So if you look at galaxy clusters, you will find a lot of these sources. And this means that there is a galaxy which is ejecting the jet at the bottom, and that galaxy itself is moving because of the dynamic nature of the cluster. Or there is cluster wind which is coming. So the galaxy is fixed, but there is cluster wind which is coming because there are cluster also goes collisions and mergers, right? And we have models for them too. This is a schematic model, but we have developed theoretical models, how to explain them based on wind's velocities, and we have a limit for wind velocities now. These except sources, which are called winged sources now, these are very peculiar because you have a core from where the jet is ejecting along the straight line, but then you have another pair of lobes or jets that are bent almost in the opposite directions. And they are tricky to understand because they can be anything that compared to, it can be simple backflow. So the jets are very underdense compared to the environment. So when a jet hits the environment, lots of matter comes back, and then because the environment is triaxial, not spherical, they can actually buoyantly affect the X-shaped radio galaxies. Or there is a simpler explanations, which is that okay, simply just accept that these are precessing jets, and you are looking from a particular viewing angle. Or even simpler, just flip your jet to 90 degree or some degree, okay, and you will get an X-shaped radio galaxy. So now the question is that if you can flip to 90 degree and you can create them, can you explain a theory where your black hole is flipping and then your jet ejection is not stopping still? So it's complicated, but we have theories for them too. Now, this is the category which I identify as miscellaneous class because it's very difficult to degenerate them, but hold on there, maybe we have a pattern. For example, if you just choose this one over there, which is very peculiar from Meerkat observations, and it's a tailed radio galaxy, but the problem is that there are two arms which is showing asymmetry. Not only that, there is a filamentary structures which is very recently discovered with sensitive telescope. For example, LOFAR, Meerkat. These filaments are the source of this filament. The origin is unknown. We have theories, of course, but it's not tested and verified. We don't know it. I was trying to model this source, and from a classical wind model, that the cluster, the galaxy group in which this galaxy resides is falling into another clusters can actually reproduce the structures. For example, if you look at here, this is kind of a 3D modeling, and this pictures represents the southern arm typically, and this is the northern arm typically, and this is the combined picture of the simulation. But one thing to notice here is that we didn't get the filament as well. So that's a flaw of the model. So again, so that means filaments need more physics, which is maybe magnetic reconnections, because the galaxy group or galaxy clusters has their own magnetic field too. So yeah, this is a very frontier topic of research, and I am also involved in doing this research. I mean, I thought that it would be easier to produce them from just flow. Maybe there is a flow which is coming and taking away the lobe matter, but I tried for two years and I failed continuously. So that means it could be a magnetic reconnections that is happening over there. Going forward, that peculiarities are very common nowadays, and you see X-shaped radio galaxies in giant scales. So that means that if backflow is happening, which has been predicted by the authors, so that means in the giant scales, meaning in the cluster scales, your cluster is triaxial in nature, not spherical. So that means recent interactions have happened, or the cluster has not relaxed yet. There are tails which are clear indications that the cluster is not relaxed, but then there are peculiar filaments, internal filaments, you see. They are coming out nowadays very often because of the sensitivity and resolution. This one over here in the bottom, it is a tail, it's a very narrow angle tail. That means the speed of the galaxy is quite high. So that's why the jet bends quite drastically. But the question is that what happens at the tail end? At the end, you have perpendicular filamentary structures, and we don't know it. Okay, we need modeling. So I was just trying to understand. This is a very toy model, I would say. What happened is, so to explain those structures, I thought that maybe the galaxy cluster was relaxed, but there is a recent interaction that was happening. So that means uh, the jet was there, which was ejecting, but then after some time, the instability, the cluster becomes involved in a merger, and then if you inject the jet, there is a perpendicular these filamentary structures that you get. But this is a toy model. A lot of things has to be tested, you know. Regarding the giant GRG XRGs that I showed you of the Cotton et al. Paper, I was trying to simulate the GRG XRGs too, and you can see the scales. It's almost it's almost like end to end is 1.4 megaparsec, and this is creating an X-shaped radio galaxies based on the triaxiality model. That the environment is triaxial, and everything happens automatically. You don't force anything. So that means okay, we can maybe use these galaxies now to understand the large scale medium, large scale environment. So that these peculiar sources can be a tool for the unexplored, because you cannot get X-ray every time. You cannot get spectroscopic distributions of galaxies every time. So maybe this is the way forward. Uh, we can also do in our simulations of the emission modeling. So this is emissions means we can produce maps for Meerkat, LOFAR, and this is just one example. When we convert into emission maps, you see there is this internal filaments that are coming up, which we saw earlier, for example, in this tail or winged sources. So basically, yeah, we are going somewhere. Now go back to the miscellaneous class again. You have another source here, which is called HIMORS. It's hybrid morphological sources. So these are very recent discoveries, but it challenges the typical FR1, FR2 dichotomy of radio jets, because FR1 jets are typically thought low power, and they show lobe type morphology, and FR2 is powerful and they show hotspot morphology. But when you see both of these characteristics in a single source, then that challenges the typical understanding of theories like, okay, it is related to jet power, or it is related to environment. Maybe everything is happening together, and there is no dichotomy. There is no maybe simple dichotomy, you know. I was just testing again another toy model. I was just testing that, okay, you see there is a cluster which is triaxial, and the center is in the bottom. But you inject a jet where one side of the jet is propagating towards heavier medium towards the center, and the other side is propagating outskirts. So you see the buoyancy creates a bubble in the outskirts, and the jet creates hot spots when it is propagating in a denser medium. But I showed this result to my colleagues, and they says that okay, other things can also be possible. For example, when the jet launches from the black hole, the immediate environment, black hole environment is quite wiggling or quite violent. So what happens when the jet, one side of the jet encounters a wind or some gas cloud, and they can dissipate your jet speed by quite an order, quite an factors. So that means maybe one side of the jet is fast and the other side is not. Now it can create your FR1 FR2 dichotomy. So yes, there are scopes of explorations. I just want to show you two more examples. These are orcs, which are odd radio circles, and people have done the simulations, and it's just the fact that the jet is stopped and you see it from a different line of sight angle. Or you can see this bottom one, which is you can see there, it's a precessing source, but it's not a simple one. There is three epoch of precision. The outer one, which you can see outer epoch. The second epoch of precision is the inner infinity shaped lobe. And the third epoch is basically typically nearly the straight one, which is J2, CJ2. So even though they are complex, this is a pen and paper calculation. So you have theories, you use your Python notebook, and then you can actually feed those models and you can understand what's happening. So we have theories exist for these sources. Now, okay, these are pen and paper theories. I just worked out one of the examples. For example, if you look at model 2, where you can collide two supermassive black holes, one has mass 1 and the other has 1/4, and you can still flip your black hole to 82 degree, which is typically observed in X-shaped radio galaxies. This is a statistics of angle distribution between the two lobes of X-shaped radio galaxies, and you can see the peak is almost at 90 degree. So yes, okay, we have theories ready. We just need to do a campaign. So basically, where Aurora is heading is this table. It actually focuses. I mean, it based on different people's interest, we have dissected the two categories. Either you focus on morphological distinctions or you focus on the extent wise distinction. So maybe you are more interested on extent, like from smaller scale. You can see if you focus on the extent, then you have FR zeros and compact steep spectrum sources, gigahertz peak spectrum sources. They die after a few parsec, a few kiloparsec. Okay, then you have galactic scale sources, then you have classical doubles, and then you have giant radio galaxies. So if you focus on extent, then morphology is an added extension. If you focus on morphology, then extent is an added complexity. So you can go either way, but the main point is that you can actually categorize these discovered sources from the survey, and then you can predict, you can produce models for each of these categories, and then you wait for escape call. So that's the plan. Just to showcase what my expertise are in this domain, I was trying to model a precessing source. This is an observed VLA image in the top part, and you see there is a core from where the jet is ejecting, and then it is ending in hotspots, which are very linear. But then from the hotspots, the lobe bend, and you can at least estimate that it's kind of showing a precision or pattern wise bending, not random. So it was our job to fit this, to produce this from a precessing source. And you can see a tentative model would be that, okay, with respect to y-axis, your jet is precessing with an angle psi, and you just look at this source from a line of sight angle theta phi. And okay, just to remind that this is a very tiny source, which is I think 2 kiloparsec, less than 2 kiloparsec. So it's happening within the galactic bulge of a spiral galaxy. And so spirals are very interesting now. They don't produce large scale jets, but they produce some interesting jets. When you model the source after some mega year, I think 3 mega year, you get these dynamical structures. But this is also something that dynamics you don't see. You see in the sky is the emission map. So we always have to we always have to, simulation people always have to come up with new tools and techniques to how to convert these maps into emission maps. So there are straightforward proxies. For example, Rybicki-Lightman classic theory, 1957, that you have density, you have magnetic field, you can convert into emissivity of synchrotron radiation, and then you can produce a map. But this is more than that. This is actually, this has particles. So while you do your fluid simulations, you have particles, small patch of particles, which follows the fluid, but wherever there is a shock, because shocks can enhance your radiation, they can capture the effect of shocks and they will be reflected back in the emissions. So when we do that, you see there is a typical matching, okay, roughly matching between the two sources. And this means that this source is precessing, which means what is happening in the core is very interesting. And I always propose people, I always say people to go and look to VLBIs, what happens to these precessing sources. And right now we have a lot of precessing sources till date. Just to give you an idea about the particle techniques, you see, this is a map basically of the particle distributions that followed the fluid of the jet. But whenever there is a hinge or bend, the particles becomes red. The color represents the kinetic energy of the electrons. And you can see that whenever there is a hinge or bend, the particles goes higher kinetic energy, which means that they are hitting or interacting with the ambient medium and creating shocks. So that means we can actually model polarization now, we can actually do spectral index now, we can actually do rotation measures and other stuff now. Just to, yeah.
In the previous slide.
Yeah.
So this is a spiral galaxy in a cluster medium.
Oh, I didn't check that, because right now the jet is 2 kiloparsec. So what is happening, what matters for us is the bulge, yeah. Yeah. So, I mean, you can even, if you have precessing source, you can complicate your precision. So this is another source discovered from VLA, and then I think later followed up with JMRT and LOFAR. And you can see clearly that there is not one single core, but there is two cores which have come because of evidence of merger we have seen. And both of them are radioactive. Jet wise, so they emit their own jet, but in fact they affect each other and then they persist in a pattern ways. And we have actually done the simulations in the right, and we created almost nearly resembling structures, which we basically predict that okay, these two cores are interacting. These are not these are supermassive black hole binary, but not the one that everybody is interested about because of gravitational waves, because they has to be in nearly to the parsec scale, which is unresolvable. So these are interesting. This says that interaction is possible. So we just need to find out more. This is if you look at the scales, this is now 16 kiloparsec. So that means it's an X-shaped radio galaxies that forms in a galaxy. So 16 kiloparsec. So you can see that we just wanted to check what happens of the triaxial nature of the galaxy, whether it can has any effect on this X-shaped radio galaxies from the backflow model. So what happens is, you see here, you have a jet which hits the ambient gas, which is 10 to the power 4 times more dense. And when you hit a wall with water, the water will split out or come back towards the center. And when it comes back, the galaxy itself divert them in the lateral directions, creating X-shapes. What is interesting here for me is that, okay, so this is basically the gray part is ambient medium. Sorry, there is too much gray. The jet is inside, basically. You can see there's an X-shaped radio galaxy jet, and the active jet, which is east-west directions, drills through the medium. And when it drills through the medium, there is shock that creates around it, which you can see in the purple color. So when you go to the X-ray observations and then you propose to see such sources, you see cavities, X-ray cavities, which is enclosed by X-ray rim, enhanced emissions. This is quite common, and people are observing them from 2000. But what happens is there is a problem right now with X-ray observations of clusters that we call them isotropic heating problem. So if you look at galaxy cluster emissions, the X-ray emissions that is coming out of galaxy clusters, if you calculate that how long, if it emit energy in that rate, how long it will survive, because when it emits radiations, it cools down, and that means it will collapse, right? And if you do a calculations, it will come out that by today, none of the galaxy clusters would have survived, and they would have collapsed. So that means the galaxy cluster is getting reheated by some violent processes, and we kind of attached it to the jet. But the problem with this jet is that these jets are very highly collimated double lobe structures. Now, how this can 360-degree isotropically heat your medium, that's the concern, because usually you see cavities and rims which are enclosed bidirectionally. So people have started to look at peculiar sources now, and they are thinking that this peculiarity, which have additional lobes or buoyancy or bending, might be the answer for this. And also, if you see the straight jet, it could be the fact that the straight jet is a right now epoch, and there were earlier epochs which you don't see because they have faded away, but they have impacted significantly, and then they finish their job, and then when it requires again, they triggers. Okay, so that means restarting sources or flipped sources or precessing sources can maybe give the answer for enhanced feedback. I was testing the same hypothesis. Now you see the scale is 400 kiloparsec, so that means it's a real cluster. And the top panel is basically the radio emission, and the bottom panel is complementary X-ray emission from Chandra band. And you can see they are most likely complementing each other. Where there is radio enhancement, there is X-ray decrement, and this is a flipped jet, almost flipped 90-degree. This is almost similar to Cygnus A, if you look at 84 mega year picture. But then I flipped the jet. I mean, in simulations you can do anything. So you flip the jet, and then what happens is you see that the energy transfer is equal, and it's almost spread at 360-degree. Do we have observational evidence? Yes, this is a galaxy cluster RBS 797, and you see there is east-west prominent cavities, and there is north-south cavities, tiny cavities, which have created because of a new renewal of jet activity, which flipped 90-degree. If you have the radio observations, you will see the flip. But also there are other examples. For example, this is a low exposure X-ray map, and you see there is an inner cavity, there is outer cavity. Also for X-shaped radio galaxies, we see these cavities, and now we have like multiple cavities also discovered. This image is just to show, this is a basically radio and X-ray overlap, and just to show you that wherever the radio plasma propagates, it affects the environment. And so, yeah, so peculiar jets could be a good proxy to understand heating effects. So basically, the environment affect the jet, but the jet affect the environment. So we can probe multiple sciences with radio jets, because as I said, getting X-ray data or spectroscopic distributions is difficult. So maybe what we can do is, because we have full sky scanned radio observations, we take them, we do theoretical modeling and predict models, and that will constrain the parameter space. Like, okay, this cluster is relaxed, triaxial, what happens in high redshift, what happens in low redshift. So basically, it will be a database for the upcoming telescopes. Another example, in simulations, you can do everything. So I was testing with the flip model, and then what I did is a jet was propagating along east-west directions, and then I forcefully flipped to the north-south directions, and this is a X-ray cavity map. And when I was analyzing it, I was like, okay, this is crazy. You cannot get a source like this. But during that time, in 2019, you get such sources. And right now in 2024, we have bunch of them, right? But the question is that, okay, the question which is very interesting is that how can your black hole flip to 90-degree and still your jet ejection don't stop? That is a question for broader community. Let us go to the straight jet part. These are called giant radio galaxies, and this is a 2025 paper from ASCAP, Australia, and it's a collage from 1.1 megaparsec to 3.8. And you can see peculiarities are also part of GRGs, giant radio galaxies. There are lots of bending, but giant radio galaxies are interesting, even if you forget about peculiarities. Why giant radio galaxies are forming? That's peculiarity, because okay, again, in simulations or in theory, you can produce a jet as long as you want because you just have to keep your jet on. But in emissions, you have to explain how the emission is so persistent up till this time, because your synchrotron cooling and inverse Compton cooling will make them vanish from your telescope observation limit. But still you see them, and not only see them, the LOFAR discovery of recently LOFAR discovery have bring the sky density of GRGs to be equal to the normal radio galaxies. So GRGs are no longer peculiar. So the point is that this is 3.8 megaparsec. These are 5 megaparsec. And you have, sorry, you have 7 megaparsec also. So I thought that let us do a campaign on GRGs as well. So I was trying to model this source, and technically I started with what we know till date, and then this is so basically you can simulate a GRGs, but I was thinking that to explain the big guys, 5 megaparsec, 7 megaparsec jet, you need lots of growth factors working together. There has to be the ambient environment to be less dense, because they are not found in the galaxy cluster center or group center. They are always found in the outskirts, in the filaments, in the void. Also, these are powerful jets. 90% of them are FR2. Also, people are finding out that their age is higher, but the confusion is which one is dominant, which one is contributing. Also, there is a fact that it could be a restarting jet. So what happens? So if you have a jet which has an epoch, and then the other epoch start in the same directions, less than 5 degree, then the next jet propagates rapid fast, and they can explain the emission problem. So you don't have any problem with emissions because the jet has not cooled yet. It is a very fresh and restarting jet. So this is a structure which I get after 70, I think 85 mega year. But the fast jet, which continued for 30 mega year, can be seen in green yellowish structures, which are there around 600 kiloparsec. And then the recent jet, which you can see with the jet's color, you can see that they are rapidly propagating and quite fast as well. They reach almost, this is one-sided, so this is almost like 3 megaparsec jet. These are quite expensive simulations, very expensive simulations, and we need GPUs to do that. Okay, just to show you how the restart works. So basically, this is how it works. So you have an earlier epoch, and then your jet renews and goes on. But the problem is that we have started with I mean, you have to also, you cannot take drastic values, a value which is not reported or known to the literature. So I was starting with the jet speed, which is defined by Lorentz factor, which is 7, which is considered to be high. I can go up to 10. But the problem is that if you look at this image, after reaching this jet to 3 megaparsec, it cannot maintain its collimations anymore. It decollimates. So that means if I run these simulations for longer, it will never reach to 5 megaparsec or even 7. It will never reach. So that means this jet is dead. So we have to come up with more advanced techniques to collimate the jet for longer. Maybe put more magnetic field, maybe put more velocity, but then how much more? I mean, that's the thing. So basically, we can predict to the observer what they are expecting. In the same time, we can also build the models. For example, if you put more magnetic field, the magnetic field are also very crazy guys. If you put more magnetic field in the jet launching, they can disrupt your jet by themselves. They call this is called as kink instabilities. So yeah, this is this is a campaign truly. I was just also working on GRGs, and I thought that, okay, GRGs might not be the fact that only large scale environment will control them. Maybe the galaxy in which they travel can also control and help them grow. For example, if you see here, this is a galaxy. The ellipse one is a galactic medium galaxy, typically an elliptical galaxy. And then I inject the jet from different angles. So you inject along the minor axis, you inject along the major axis, and then intermediate axis. So you see, if when I give them more resistance to the flow, they create an X-shaped radio galaxies. Whereas in the minor axis directions, it's a classical double lobe radio galaxies, but it's quite fast. If you compare the time, that's like almost half. So that is almost like 32 kiloparsec source already. It's a considerable one. So you might say that okay, 2 times is not fast enough, but 500 megayear versus 1 gigayear matters for GRGs. So for example, this is the same as this one, which where the jet propagates along the minor axis, but we just increase the collimations and thrust by little bit. The jet power for both of them are same, but we strategically, so there is a okay, the 3-4 parameters jointly produce the jet power. So you can increase a bit and decrease other parameters a bit, and you can do this. This is again 2 times less in time than what we have. So yes, so it has several growth factors to explore further, and we can work on collimations and stuff. But the ultimate goal for GRG people to do 7 megaparsec jet, which we can never maybe simulate till after, I mean, upcoming 5 years. But I convinced some people. We got some GPU time, high GPU time. So I am at least gonna go up till 5 megaparsec, and see what we get there. Okay, so I think I'm in the end. This is the Aurora project. It targets distinct sources because they give more physics, but it cannot be done alone. So we need help wherever we can. Thank you.
Thank you so much.
Yeah.
It's a great talk. Any questions?
Yes.
Yours.
Wondering if you can go back to the previous image of your 7 megaparsec
Yeah.
jet. Is it really convincing that it's all actually linked, like one structure or related, or could it be that they're
Yeah.
along a galaxy filament and actually some other source? I don't know. I'm just wondering how.
Okay, so the people who reported it are actually a big group, very big group with very recognized names over there. And they have actually worked out, not for this paper, for the entire 3 to 4 years to develop an algorithm to come up with a convincing fact that okay, whether they are joined, and whether they can disentangle the projection effect to understand the true length. Yeah, they have written a paper on that algorithm. I have tried to read it. I didn't understand it, but they have reported it. So I mean, to me, I think it's quite convincing. I would not doubt it because just in 2020, just in 4 years ago, people were never finding jets which are more than 5 megaparsec. Whenever somebody discovers largest jet ever, the level always reach 5.01, 5.05. So people start to believing that okay, that's the limit maybe. So 5 megaparsec is the limit. Now we have 7. So we don't know. We should not doubt it and explore theoretically basically. We can predict for 10 megaparsec jet that if somebody finds something from SK someday, 10 years later, there should be a database to match with theory. Yeah.
Right. I see one question online. I think it's Nadim. You can go ahead. Hope we can hear
Okay,
you.
thanks. Yeah. Thanks, Gaurav. It's really great work that you're showing. I joined in a bit late, but I don't know. In your simulation, we know that, for example, AGN somehow, okay, they stop and then they get reignited. And in some of those giant radio sources, we do see kind of like this double feature. How do you parameterize, okay, what's the cause of those reignition on and off?
Okay, so there is This is a very frontiers questions, I would say. Right now, what I am doing is that I am modeling the large scale features. So what my jet is that what I do the modeling is that I just adopt restarting ages from literature reported values, and then
Okay.
that is a parameter for us, and then we see what happens in the larger scales. To truly understand how the restarting is happening, we have to go to the black hole code, black hole accretion codes. So these two codes, these two domains are completely different. So you cannot follow something from black hole scales to these large scales. So the one way of answering is that in my code, you can model them as assuming parameters, restarting age as a parameter, and what happens in the larger scales. And once you get your parameter values, now you go back to the black hole accretion codes, and then you test whether this is even possible. Yeah.
Okay. Okay. Thanks a lot.
Yeah.
That was my question too. Okay, another question online. Paul, please go ahead.
Hi, thank you for the talk. I think it's a really
We
fascinating.
can't hear you properly.
Yeah.
Well,
Doesn't seem like I can talk my question.
can you please post it maybe on the chat because
We cannot hear.
yeah, it's really weird the way that we can hear you actually. Okay, so in the meantime, I was also wondering about these jet flips that you were talking about. So do you know, like, is there any known physical cause for that, or is it also something related to the black hole accretion?
No, I mean, yeah, of course. I mean, the flip, whenever we see a flip, it has to happen. It has to happen with the black hole. There are theories, two theories, which I have worked it out. There is inhomogeneous mass accretions. That means your accretion of matter is not smooth. And suppose if a merger happened, okay, and then suddenly a sudden amount of gas is channeled, and then because accretion disk and black hole orientations are connected, so if something happens to the accretion disk, it also affect there. So I have calculated a theory, and I have got 70-degree flip. But also you can have smaller scale black hole collisions between them together, which would be very interesting for a broader community. Yeah.
Okay,
Yeah.
that's interesting. Right. I can see Nadim is posting a question.
Yes.
Okay, so thank you for the presentation. Any thought or comments on magnetic fields being the cause of jets bending or causing rotation of the jets?
Yeah, I mean, magnetic fields are very culprit, I would say, because they govern a lot of radiative features of the jets. If you put more strength in magnetic field, they can bend your jet, but I suspect they cannot produce precision. Because if they bend it, the bending would be abrupt and quite irregular, because that's a perturbations for magnetic field, and perturbations are random. Whereas if you look at continuous pattern in your jet, then I would think that precision would be a better model. Yeah.
Okay. Let's get one, yeah, in the room, and then
I was wondering, when you have your restarted jet, is it the case that the first jet kind of cleared out the medium, or like affected the density of the medium, and then that's why the second one
is you gave me the answer.
Okay.
So basically there is a cavity, and that cavity helps the second jet to propagate faster, and that could be one of the reasons for GRGs, or in general for large scale jets. But if that is true, then the question is that the current fraction of DDRGs we know, double radio galaxies, may be quite high, especially the cluster sources. As I told you, isotropic heating is a problem. So yeah, we need to work on DDRGs a lot. In fact, we need to work on everything a lot. Yeah.
okay, let's see. Nadim has another question. Do you have a way to get dynamical age of the extended sources from your modeling?
Actually, in our simulations, we get dynamical age right there. whatever age we get, that's the dynamical age. So to compare with the observers, which they predict the spectral age, we use our emission mechanisms, emission tools to get the equivalent spectral age. So we can compare dynamical and spectral age, but in simulations, we get the dynamical age directly.
Okay. No, I mean, my question is because I know people working on giant radio sources, they all use like a package which was written in the 1980s, and nobody have access to that. And
Yeah.
we don't know
Yeah,
what it
yeah.
does. Like Dynage, I've not seen any source code of that. And I
Okay.
was wondering if maybe it's time for us to make something
We
publicly
can
available.
actually I was following Machalski or their group. They have given out the theory.
Yeah.
So I have those theories, you know, and I have worked out a Python code on that.
Oh, that would be
And
great.
to model it better, I think we can combine simulations informations there, and think we can develop together our own code.
Okay, yeah. Please make it public available because everybody has to
Okay, all
contact
right.
them.
That's the goal for Aurora.
Thank you.
Yeah.
Okay. No more questions. All right.
All right.
Thank you, everyone. Thank
Thank
you,
you.
Gaurav, again. It was really fascinating. Thank you, and see you in the next colloquium.
Oh yeah. See.
Thank you. Bye.
Bye bye. Okay. Where am I?